Okay. So basically, so till week 4. Okay. So week 1 to week 4, it is all about basics. Okay. So basics of signals and systems. Okay. And Laplace transforms. Okay. Then time domain analysis. Okay.
Okay.
Next, week 5 to week 11. Okay. So basically, week 5 is about controllers. Okay. So controllers in this sense. So uh, we have studied about P controller, proportional integral controller, proportional derivative controller, PID controllers.
Okay. Can
Okay.
you spend
So,
some time on what are the other? I mean, I have gone through the lectures. It is
yeah.
very vast, but can you just summarize your view on this week 5?
Now, basically, in controllers, what we do is if you consider, okay, so you have your plant, okay, so plant will be represented with G of S, okay,
That means system, right? Up until week 4, we
yes,
are
yes,
calling that system.
okay.
Okay, at least in signal
Then you
systems, we are
have
calling
your
that system.
output here, okay. You have your reference input.
So plant and system are interchangeable, right?
Yeah, it is same.
Okay.
System and plant both are same.
Okay.
Okay. So you have your input R of T, reference input. Okay.
Okay.
So then you will take the feedback. You have your feedback system H of S. Okay. In terms of transfer function. So then this summing point, it will compare both. So the signal from reference input R of T. Okay. Then y of t given to this H of S. Okay. Then we get some output here. Okay. Let us say that output is some A of t. Okay. So then we get error here between these two signals, which is nothing but R minus A. Okay. That error we give it to the controller C of S. Okay. Basically here C of S is nothing but, okay. So if it is proportional controller, okay. If it is proportional controller,
Okay. Okay. So
yeah.
we are
So
taking the
just a minute.
feedback H of S and we are comparing
Yeah.
that with the input reference input, and
Yeah.
that is nothing but error. Okay.
Yes,
Now
yes.
we are
If
in the
it is a
proportional
proportional controller, so the C of S will be some constant K.
times R
Okay.
minus A.
We call that is as KP. Okay. If it
Okay.
is PI controller, then this will be KP plus some KI by S. Okay. If it is PD controller, this will be KP plus KD multiplied S. Okay. If it is PID controller,
KP
okay,
plus
so
KI by S plus KDS into,
yes,
yeah.
yes,
So that is the
yes,
value of the C of S. C of S. Huh?
yes, exactly, exactly.
Okay.
Okay,
In that case,
then
C of S.
you give, so the C of S input is to the C of S input is E of t. So output is the U of t, which is nothing but controller input.
Okay. So one
We
second, one second, one second. So here U of t in the first case it will be Kp into R minus A, right? U of t.
no, 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 not exactly, not exactly. Okay, so here C of S is nothing but, okay, U of S divided by E of S. Is this clear now? Okay, in Laplace transforms.
U of S. One second.
U of S is the Laplace transform of this.
Yeah, U of S is equals to
And
E of S into C of S, right?
yes, exactly, exactly.
Okay.
Okay, we call this U of t as the control input.
Okay. So what will be the
Mm.
C of S
Mm.
for proportional controller? It will be KP.
Yeah, tell me.
So C of S is
This it
KP
will
for the
be KP
proportional controller,
constant.
right?
Yes, yes,
Okay. So
yes.
in the first case, U of S by E of S is equals to KP, na?
So exactly. So In first case, what will be your u of t Laplace inverse of C of s E of s, correct?
Right.
Right. So that is Laplace inverse of kp multiplied E of s. That is kp multiplied E of t. Clear?
Right. Right, sir.
Okay. So in the same way, we proceed with the others also. Okay. In each case, what we do is we find this expression for y of t. Okay.
Okay.
In each case.
Okay.
Okay. So
Uh-huh.
expression for y of t we will find. Okay. That expression then we will plot. Okay. T versus y of t. Okay. Let us say
Okay.
if you consider r of t as the step input, the value will be 1. Correct?
Right.
So yeah. So that will be like somewhere here. Okay. Then
Right.
the y of t, it goes like this. Okay.
Mhm.
So in each case, we find this y of t. Each case means proportional controller, PI controller, PD controller, PID controller. Okay.
Oh, can you repeat your
In each case, we find this y of t.
last statement once again, sir?
In each case, when C of s is Kp, we find y of t. Okay. When C of s is
Okay. Okay.
Pi, Kp plus Ki by s, we find y of t.
Mhm.
When C of s is Kp plus Kds, we find y of t. That means that will
Right.
become PD controller. Okay. In each
Okay.
case,
Okay.
once we find y of t, so you'll get forms like this, different waveforms, correct?
Okay.
So in each case, we will check what happened to the parameters. Parameters of percentage overshoot, rise time, settling time, steady state error, etc. Okay.
Okay. What are the parameters that we learned up to fourth week?
Yes. So first we will find that the proportional controller will do maximum job. Okay. But the steady state error would exist. Clear?
Okay, sir. Quick thing. I mean, what are the ideal? I mean, okay. I mean, ideal will be different. Best value. Okay, ideal values of.
No, 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 no. Different. Listen. When
Okay.
you
Okay.
take proportional controller, that is
Mhm.
KP, okay, you will find that the y of t will reach 1. Okay. But not exactly. So you will find that there is some steady state error. Clear?
Okay.
Then you will go to PI controller. PI controller, what it does is it removes the steady state error. It will make the error to 0. Okay.
Okay. Okay.
Then, but it will have some steady state output value. Okay, sorry, it will generate some
Oh.
overshoot.
Overshoot.
Okay. Then we
Okay.
take this PD. The PD
Okay.
will solve this overshoot problem. Okay. So
Okay.
ultimately, the T controller will try to reach the value 1. This PI, it will remove the steady state error, where PD, it will solve the overshoot problem. All put together,
Mhm.
okay, we'll get to all the advantages. That is
Okay.
nothing but this PID controller.
Okay. We'll get. It is. It will. PID will address overshoot to TS and ESS, right?
Yes, yes, exactly.
And what about TR, sir?
Sorry? No, TR is
TR.
the part of this one only.
Rise time will always be there, right?
Yeah, yeah. Rise time is the included connected to percentage overshoot. Okay.
Okay.
So in each case, what you need to do is you need to find this y of t. Okay. So let me show you a simple example. How do you do this? Okay. Quickly. So we have this C of s. Okay. So you have this G of s. Okay. So you have y of t. Let's say you have h of s. Okay. So then we have this minus r of t. Yes. Okay. So let's consider this is K. Okay. So this is some 1 by S plus 1. Okay.
Proportional controller, right?
This will be 1, let us say. Okay.
Okay.
Now,
Okay.
so generally, what is the y of s by r of s here? Can you tell me? So y of s by r of s, that will be like gc by, okay, 1 plus gch. If you do the calculations, you will get it like this.
What is GC, sir?
Gc means G means
Okay.
this one, C means this one.
Okay. Okay. I thought GC is one term. Okay. Yeah. Yeah.
Okay,
It will
so
be
what
like
is, what is this one? It will be like 1
G
plus
by 1 plus G
1
into
by
beta.
s plus 1 plus 1 by s plus 1. Okay, what
Yeah.
is it like? 1 by s
Sir,
plus
K,
2.
you have to add K also. K by S plus 1 plus what?
Exactly. Sorry. Okay, so that
Yeah.
will be like
1 plus K.
that will be like k by
S
s
plus
plus
1 by 1 plus K
1
by
plus
S
k.
plus 1. Yeah.
Correct. Now, let us say R of S is unit step. So its value is 1 by S. Okay.
Okay.
So what is Y of S? Y of S is 1 by S. 1 by S multiplied K by S plus K plus 1. Am I correct?
Yes, sir.
So this you can write it like A by S plus B by S plus K plus 1. Am I correct?
Yes, sir.
Okay. So now you
Uh-huh.
can find the A and B values. Then you can take the inverse Laplace to get Y of t.
Yeah, it will be A e power minus
It
S
will be like A u of t plus B e power minus K plus 1 t.
1 into U of t.
Okay. Yeah. It is like this. Okay. So that means if you plot it, okay, so you'll get some waveform. Correct?
Uh-huh. Uh-huh.
Yeah. So then you'll be checking these values.
Okay. Okay.
Okay. So
Uh-huh.
you are supposed to reach 1. Okay. But with proportional controller, you will get the response like this. Okay. So you'll have some ESS.
Okay.
Okay. So
Okay.
then if you replace this K with K plus K by S, let's say K1 plus K2 by S.
Yes, sir.
Okay. If you do the same process again, find the Y of t, then you will get like this,
Okay.
where
E
the
of S
steady
is
state
55.
error goes to 0, but you will get some overshoot.
Okay.
Okay, then you replace with K1
T.
plus K3. Yes. Okay. So you will get something like this. Okay.
Okay. Okay.
So it's like this. So now again we replace with K1 plus K2 I K2 by S plus K3 S. Okay, you'll
Okay,
get
sir.
the proper response. Clear?
Oh, okay, sir. Fine.
That is how
Yeah.
you need to proceed. Okay.
It's
Yeah.
very nice, sir. Thank you.
Uh,
So this is the summary of the week 5, right?
Yeah, it is the summary of PID controllers. Okay.
Okay. Apart from that, I mean, are there any important I mean, I have gone through the lectures. I will go through them. I mean, I'll go through the
Yeah,
slides.
this is the idea. This is basic idea.
Okay. The entire week 5 revolves around this idea, right?
Yes, exactly. So in each
Okay.
case, we take first P and we do the entire derivation, because I took here the simplest example.
Okay, sir.
Okay. We do the entire derivations in all the cases. Okay.
Okay. Yes.
Yeah.
Fine.
So
Thank you.
it considers PI, PD, etc. all the controls. Okay. Yeah.
Okay, sir.
So coming back to today's live. Okay. So basically, we are in week 9. Okay. So week 9 is about
Sir, we will spend on up to we'll spend time on quiz, sir. Week 10 we can take it because the syllabus is quite huge for week quiz 2.
sorry.
The syllabus is quite vast for week 2. We'll spend on week
Uh,
1 to week 8, sir.
for what?
For the we will spend time on week quiz two, sir.
No. The issue is that it is again the same thing. Last time we missed that week 5 1 live because of revision class. Okay. So now if we don't cover this week 9 here, next again we'll miss that. So that's the issue. Anyway, so if you have any doubts, you can ask me on Friday's class also.
Okay,
Not
sir.
an issue.
Friday will be
Yeah.
revision class, right?
Yeah, I'll be taking that.
Okay, and it will be
Okay.
revision class, right?
It's not revision class because generally we don't conduct revision classes. Okay, until unless the request comes from the students.
We'll take a, let's have a revision class, sir, from week one to week eight,
Yeah,
because
you better write one email because it is not part of the schedule. So you write email, then we'll discuss with the other instructor and try to take some revision class. Okay.
okay, sir. Okay,
Yeah,
because
yeah.
you understand, right? Because from week
No.
five,
Now here I'm today I'm discussing not discussing the week 9 content. Instead, week 8 and week 9 are related. So that's why
okay,
I'll try to cover content of week 7 only. Okay, so
okay,
that it will be also useful. Okay.
okay,
Yeah.
okay.
So basically, the week 9 is about the design of controllers, design of controllers or compensators based on frequency response. So frequency response. Basically, if you see the previous live or last week lives, okay. So that is this design is based on the root locus. Okay. So this is based on the Bode plot. Okay. So basically in root locus, what we do is, okay. So we will get the design requirements. Okay. So we will get design requirements in this sense. I want my percentage overshoot this much only. I want my transient time, the rise time this much only, settling time this much only, steady state error this much only. Okay, these are design requirements. The example, it is like I want my percentage overshoot is 20% only or 5% only. Okay, then rise time has to be this much, settling time has to be this much, etc. So then what we do is, okay, so what we do is we already know the formulas. Okay, so rise time, let me give the rough formula. So I by omega d, okay, then settling time 4 by zeta omega n, then percentage overshoot, it will be like 100 e power minus zeta pi by, okay, root over 1 minus zeta square. Okay. So these are different formulas we have. Okay. Now what we do is using all these formulas, okay, what we do is based on the design requirement, since the design requirements are fixed, these values are given to you. Okay. Then we will find, okay, zeta and omega n. We will find zeta and omega n using these equations. Once we have the zeta and omega n, okay, for second order systems, okay, for second order systems, so what is it? Zeta omega n plus or minus j omega n root over 1 minus zeta square. These are the poles location of a second order system. Correct? So we can substitute the zeta and omega n here and we get the poles location. We call these poles as the dominant poles. Dominant poles. Is this clear? Any doubt here? Any doubt in this? Basically, what we do is for any controller problem, we will be given with design requirements. My overshoot has to be this much, rise time has to be this much, settling time has to be this much. So from time domain analysis, we have these formulas. Okay, using those formulas, we will find zeta and omega n. Then for a second order system, we have this equation, okay, which will give you two poles. Okay, we generally call them as the dominant poles. Once we have these dominant poles, what we do is, Okay, so we
Dominant pole
plot.
is the
Ah,
dominant pole is the pole that is close to the y-axis, right?
yes, exactly. Okay, so once we have these dominant poles, what we do is for the given system, we will draw the root locus. For the given system, we will draw the root locus. For example, let's say my root locus is something like this. Okay, then if my dominant poles are like this, okay, if dominant poles are like this, what we will do is we will try to shift the root locus. We'll try to shift the root locus. Okay, we'll try to shift the root locus. Let me write it here.
Thing, sir.
Okay, yeah.
We have, I mean, all this is in what you call S-plane,
Ah,
right?
in S plane. Yes, exactly.
So we have the poles on the, I mean, we know that, I mean, if the poles lie on the left half of the plane, the system, okay,
Mm,
uh,
mm,
we have open loop system, and if the
mm,
poles of the open loop system, they lie on the left of the, we,
mm,
the,
mm.
if the poles of the let's take a system h of, I mean, the forward, okay, there are two things here: open loop and closed loop. The open loop system is the
Mm,
open loop gain is g of c, and the
mm.
feedback feedback path is h of s. So the
See,
closed
see,
loop system becomes
see, it is
1
like
plus
this. It is
g
like
of s
this.
minus g of h.
Listen,
No,
listen,
the
listen.
thing is, yes,
Ah,
sir. Yeah,
listen
yeah,
first. Listen first.
yes,
Let
sir.
me tell you. So let us say this problem is given to you. Okay, this problem is given to you. Okay, so
Mhm.
the g of s is given. Okay, now my question is to asking you to design a controller. Okay, once you design this controller, this output. Okay, if you plot the response, something like this. Okay, my output should have this much overshoot, this much transient time, this much settling time. Okay,
Okay.
this is my design requirement. Okay, so
Okay.
once I design my controller CFS, okay, so if I put that controller over there, it will give you some output, correct?
Right.
That output should get these values. Okay, so
So
the
we are
question
talking about
is
closed loop systems only, right?
closed loop only.
Okay.
Okay, the
Now
question
these
is
poles are there, right? These poles are for closed loop or open loop?
closed loop only.
Closed loop only.
Yeah. So the question is, how do you design that CFS? Okay. So which will give you these values. Okay. That we call it is as a design of controller. Okay.
Okay, there
And
are
the
two things
this
here. One is, I mean, to kind of,
uh,
achieve stability, we'll be having a feedback path, and to achieve
mm,
even more stability, we'll be having the controller. Two things, right?
yes, exactly.
Okay.
Basically,
So,
control system course is all about to design this CFS.
okay.
Okay, to design to meet these design requirements. Okay,
Okay.
that we call it is as a design of controller. Okay, so the techniques so far we learned are root locus and Bode plot. Okay, so using
Then
these
what is
two
the significance of feedback path, sir?
feedback, if there is no feedback, you apply some input, you get some output. Okay, there is no correction in the output. You want
Okay,
it to you want yeah
the system that corrects the feedback signal is controller. Huh? Okay,
yes exactly.
okay,
Okay,
that's what.
yeah.
See,
So
yes,
we
sir.
know these two techniques, root locus and Bode plot. Okay. So we will design this controller using these two techniques, root locus and Bode plot. So till last week, okay, we have already seen the theory behind this root locus and Bode plot. Now, how do we use those plots to design this controller? Okay. Last week, madam has explained the design using root locus. That's what I'm trying to recapping here. Okay.
The
So,
definition of root locus is
mm,
how the, I mean, locus is like, I mean, how the roots of a system uh, will travel. I mean,
Yes, exactly. If you take your controller as, let us say, proportional controller, okay? So you have your closed loop transfer function is like this. If you vary your k from 0 to infinity, okay? For every k, what will be the pole's location, okay? How do the poles travel? When you
okay.
start with k is equal to 0 till k is equal to infinity. That is called as the basically root locus. Okay.
Okay.
So in
Does that
previous
have
modules,
any relation
we
with the
have,
pole?
you have to find the poles every time.
No, no. Like, I mean, is there any relationship between the root locus and the poles?
Root locus itself is the transition of poles. So when k is
Okay.
equal to 0, you have poles here. When k is equal to 1, you have poles here. K is
Okay.
equal
Okay.
to 2, you have poles here. So you vary from k is equal to 0 to infinity, you will get this path.
Okay. No, no. You have marked poles a little aside from the root locus, right? So I was just.
Now, these are dominant poles. Okay. These are dominant poles. Okay. This came from this
So
equation.
dominant poles are nothing but poles that will anyways lie on the root locus only, right? For one value, some
No,
value
no,
of
no,
k.
no, not exactly. Not exactly. The dominant poles, they came from zeta and omega n, this equation. So zeta and omega n, they came from the formulas of TR, TS, and MP. Okay. Once you know TR, TS, and MP from the design requirement, okay, you're calculating zeta and omega n. Zeta and omega n are the design requirements. Okay. From
Okay.
there, you're calculating your dominant poles. Okay. But basically, your system poles will transit like this. But your dominant poles are here. Okay. Now your controller pitch in and move your root locus. If you design the root locus properly, okay, it will move your root locus to cover the dominant poles. Okay. Is that clear?
Okay, sir.
It will shift the root locus to cover the dominant poles. Once you
Anyways, you
cover
will be
the
sharing this
dominant
PDF.
poles,
Anyways, you will be sharing this PDF, right? The
yeah,
recognition,
I'll share
right?
this PDF. Yeah.
Okay. Okay.
Okay, once your root locus will cover these dominant poles, then your design requirements are uh, emitting already. That's the idea. Okay. Here, what we are doing in the root locus is your design requirements are percentage overshoot, rise time, and settling time. Okay. Using those and root locus, you are designing the controller. Okay. Now,
Okay.
same thing, same thing in the frequency response. Okay. Particularly using the Bode plot. There also you'll have the design requirements. Okay. So the
Okay.
in frequency response, the design requirements are in terms of the uh, peak, resonant peak MR, okay, and resonant frequency omega R and bandwidth omega B. Okay, so what are these? So this is resonant peak. Okay, so this is resonant frequency. Okay, this is bandwidth. Okay, so you'll have the formulas again. Okay, for these also. So MR is like 1 by 2 zeta root over 1 minus zeta square. Okay. Similarly, the omega R is so omega n root over 1 minus 2 zeta square. Similarly, omega B bandwidth. Okay, so that will be like omega n root over 1 minus 2 zeta square plus, so 4 zeta power 4 minus zeta square plus 2. Okay, so these are the formulas we have. Now, design requirements are given. That means my peak overshoot, my resonant peak has to be this much. My resonant frequency has to be this much. My bandwidth has to be this much. So that means these values are given. Okay, now the left side values are given. Now right side, what you do? So using these equations, you find zeta and omega n again, just like here.
Do we need to remember all these formulas, sir?
No, not needed. In exam, we don't we don't need to remember the formulas, not much.
But I mean,
Okay.
their application. I mean, to find the values, we have to
Yeah.
remember the.
No, not much. Because this kind of formulas, you don't need to remember, but simpler formulas, you have to remember. Okay. These are regular usage formulas.
Okay,
Okay.
these formulas will be
So,
given in the exam.
sorry.
These formulas, I mean, they will be given the bracket in the exam if there are
Yeah,
any
yeah, yeah.
questions.
Whenever there is a complex formula, so the formula will be given. Okay. If it is very complex.
Okay, up to
Okay.
week 4 formula, if you remember, that's fine, right?
Yeah, you have to remember these things.
So,
Okay.
up to week 4, they are week
Anyway,
4 formulas only.
professor will give the question paper. It's not me. Okay. So
Okay.
they know those things. Okay. So now the idea here is these are our design requirements. Okay.
Mhm.
It means these values are given to you. Okay. Using those values and formulas, you will find zeta and omega n. Once you have this zeta and omega n, so what you do is just like here, okay, just like here, we have plotted root locus. Okay, here what we do is we will plot the Bode plot. What is Bode plot? So the Bode plot is
Magnitude and
magnitude
phase
plot
margin,
as well as the phase plot. Okay,
phase plot.
the magnitude plot is, let's say, something like this. Okay, the phase plot is, let's say, something like this. Okay, now what we do is we will check the gain margin and phase margin. So they will be functions of this zeta and omega n. This zeta and omega n. Okay. Now we will check whether this zeta and omega n, we will find this gain margin and phase margin. Is there anything we need to shift? Okay. Shift this Bode plot. Like we are shifting here root locus. Okay. So we need to shift this magnitude plot or phase plot to meet these design requirements. That is the idea. Is this clear? Any doubt?
Okay.
Yeah. So that's the overall idea of designing the controller using Bode plot. Okay. Now what I'll do is first to go with the design part. Okay. First we need to understand and do some simpler examples. Okay. The examples are like how to calculate this. First of all, how to draw this Bode plot, which I have already explained in the previous slide. So you can see them. Okay. Once we draw this Bode plot, how to find this gain margin and phase margin. That is first thing. Once we have this gain margin and phase margin, then you can think of the shifting these blue to red. Okay. Now what I'll do is I'll do some examples with finding the gain margin and phase margin. So that you'll have clarity. Okay. So let me take up one example. Yes. Okay. So here, so assume that I'll be going with basic again. Okay. So the Bode plot. So basically, we draw the Bode plot for the open loop transfer function. Open loop in the sense, so we have controller and we have plant. So the controller is G. Sorry, the plant is G, and the controller is, let's say, GC. It could be a P controller, PI controller, etc. Okay. Generally, we define the open loop transfer function as multiplication of these two. That is nothing but this one. Okay. We always draw the Bode plot for the open loop transfer function. Okay. So what is Bode plot? Bode plot is, consider the same.
For a closed loop, right?
Root locus?
Bode plot we draw for the open loop. And
Root locus also we will draw for the open loop transfer function, but it will talk about the closed loop ones. Okay. So here,
so if the feedback is one, it will talk. If the feedback is other than one, then if h of s got
that's the beauty of the root locus. Okay, so you go and check the example, you will understand it. First, you will start with the open loop transfer function and follow all the steps of root locus. Finally, that K will be included there. Then it will talk about the closed loop price. How they are changing. Okay.
So you mean to say that root locus is completely independent of the feedback, huh?
No. Feedback is part. Feedback is part of that.
Feedback, no sir. Root locus assumes the feedback is one.
No, not like that. Feedback could be anything. In general, in problems, we take one, but it could be anything.
Okay, sir. Let's go ahead. I'll try.
Yeah. So we have this open loop transfer function. Substitute S is equal to j omega. So then we have GC j omega, G j omega. So Bode plot consists of two plots: magnitude plot, which is 20 log that open loop transfer function, and then phase plot is angular. Okay. So on the x-axis, we'll have the frequencies. Okay, frequency starting from omega is equal to almost 0 to so a higher value. Okay, so you start with this example. No. First, this picture says the definition of the gain margin and phase margin. If you get any doubt, you can ask me. First, concentrate only on this left side. Okay, so only this part. Concentrate only on this part. Okay, here we are defining two things. Okay, if you get any doubt, you can ask me. Okay, you are defining two things. One is gain margin. Okay, another is phase crossover frequency. Okay, first what we do is we draw the Bode plot. Drawing Bode plot means what? Draw the magnitude plot and phase plot. Am I correct?
Plot. Yeah.
Once you draw that, okay, what you do is, okay, in the phase plot, see where you have this minus 180 degree line. Okay. Once you find this minus 180 degree line, draw this right line. Okay. So once you'll find this point. Okay. From this point, find what is this frequency. Okay. That frequency, this coordinate is nothing but omega PC minus 180. Is this clear?
Okay, sir.
Yeah. That will be your phase crossover frequency. Okay, phase crossover frequency is the frequency when the angle is minus 180. Is this clear? That is the phase crossover frequency. Okay. Now what you do is, from your phase crossover frequency, extend that line to the magnitude plot. Okay. Extend that line to the magnitude plot and check where it is touching your magnitude curve. This is the curve. Okay. So now check its horizontal line. So horizontal line has how much? Minus 10 here. Okay. Minus 10 means how much it is deviated from 0? 10. Correct? This part.
Okay.
Okay. So that will be your gain margin. Means if you push your curve by 10 dB up, okay, you will reach 0. Is this clear?
Yes, sir.
So that is your gain margin. The gain margin in this case is 10 dB. Okay, sometimes what happened is you may get your curve like this. Okay, in that case, your curve is 10 dB up. Am I correct? From the 0. In that case, it will be minus 10 dB. Okay, so these are the two things. Okay, what are the two things you have? So first one is the phase crossover frequency and gain margin. Phase crossover frequency as well as the gain margin. Is this clear? What you do is first find the phase crossover frequency, which is nothing but the frequency corresponding to minus 180 degree line. Then extend that line, okay, till this point from the phase crossover frequency and check how much it is deviated from the 0 dB line. That is your gain margin. Is this clear?
Okay, so, sir, I'll write. Yeah.
Phase crossover frequency and gain margin, two things. Okay. Now, similarly, in the second side, you'll be defining two things: gain crossover frequency and phase margin. Okay, so same thing. What you do is now you start with the magnitude plot. Okay, from 0 dB line, draw a straight line. Okay, and find this point. Okay, so once you find this point, extend it down. That will be your gain crossover frequency. Okay, once you have gain crossover frequency, extend that one further to the down to the phase plot. Okay, and check this point. Okay, so the point where the gain crossover frequency is connecting. Okay, now see how much it is deviated from minus 180-degree line. Okay, that will be your phase margin. Okay, phase margin is P plus 180. Okay, so you have to find that P exactly. Okay, how much you add that? Okay, that will be 200 minus 200 plus 180 in this case. Okay, that will be minus 20. Is this here? Finding gain margin and so this is gain crossover frequency, phase margin.
Okay, sir.
Okay, yeah. So two things very important. Okay, first one is phase crossover frequency gain margin, gain crossover frequency phase margin. Okay, so we'll be using the same Bode plots, magnitude as well as the frequency plots. In general, what we do is, if both are positive, we say system is stable. Okay, we say system is stable. Okay, if both are negative, we say system is unstable. Okay, so how these, how they are stable or unstable, you should go back and see that videos, search video. So he has explained nicely. Okay, so I don't have much time to repeat that explanation here. So assume that if both are positive, okay, if both are positive, system is stable. Otherwise unstable. Okay, both are negative. Okay, now let me show you an example how to do these calculations. Okay, start with this example. Okay, you have g of s is this transfer function. Okay, now our job here is to find the gain k. Okay, what value of k? It will give us the gain crossover frequency is 5 radians per second. That is our question. What is the k here? Okay, so using Bode plot, we have to find what is the k, which will give us the gain crossover frequency is 5 radians per second. Okay, first what we do is we will draw the Bode plot completely. Then we will find this gain crossover frequency. Okay, so then we will find that k value. Okay, let us go step by step because these steps I've already explained previous live also. So I'm going quickly. Okay, you can check this. So first step one. So take g of s. Okay, so put it into this format and check what is T1 and what is T2. Okay, then substitute k is equal to 1 for a moment. We draw the Bode plot for all k is equal to 1 first. Okay, substitute s is equal to j omega. Then form this table. How to form this table? I have explained very clearly and easiest way in the previous example. You should see exactly. Okay, you have two zeros. Okay, that's why slope is plus 40. You have two poles. Okay, which will add, each one will add minus 20 slope. Then the slope changes from plus 40 to minus 20 is plus 20 slope change. Then slope changes from plus 20 to minus 20. The slope of is 0. Okay, you can check these calculations, you will understand it. Once we have this, what we do is we will choose some lower frequency because from here we have omega C1 and omega C2. Okay, first what we'll do is we'll choose a frequency which is less than the omega C1. Okay, here omega C1 is 5. Okay, we choose some frequency of this one, 0.5, which is very, very less than the 5. Okay, then we calculate the magnitude A. Okay, for both at omega L and omega C. At omega L, we got the magnitude as -12. Omega C, we got the magnitude as 28. You can check these calculations later. Okay, that is step 3. The next step 4 is, so you do the calculations at omega is equal to omega C1. Next at omega is equal to omega C2, which is nothing but 50 from the table. Calculate again, you got 48 dB. Okay, next, so that is the second cutoff frequency. Next, you choose a frequency of higher frequency, which is very greater than omega C2. Omega C2 is 50. Okay, you are choosing that as omega H as 100. Again, at omega is equal to omega H 100, calculate it. You got 48 dB. Okay, so how you are doing? These are the two corner frequencies. You choose one frequency very less than the omega C1. You choose another frequency very greater than omega C2. For each frequency, you are calculating the magnitude. Okay, similarly, the phase plot also. This is the angle corresponding to the transfer function. Okay, so when omega varies from 0.5 to 100, this omega L to omega H, for each value, find this phi. Sorry. For each value, find this magnitude. Okay, so these are the two things. Very important. Now you can plot this Bode plot. Okay, magnitude as well as the phase plot. Clear? This you can check it again. You see my previous live and come back here, check the values. Okay. Now come back to the question. The question is to get omega GC as 5 radians per second, what will be my K value? That is the question. Okay. So how do we calculate? Okay. You can see this gain crossover frequency, basically what it says. Okay. My line has to be 0 dB line. That is with 20 dB. Okay. When you take only GC, it will be log 0. That value is 1. Basically, this is the 1. Okay. So that will be 0. Okay. So in this case, okay, omega GC is equal to 1 radians per second. For K is equal to 1. Okay. But what we want is omega GC is 5 radians per second. Okay. At that time, we wanted to get this is equal to 1. Okay. So now question is, what is my K value for this case? Okay. So simply what we do, so 20 log K is equivalent to minus 28. Okay. The K is equivalent to 0.0398. Okay. So at that point, okay, so the magnitude is minus 28. Okay. So that is basic one. Okay. Similarly, you can check the other problem also. In this case, what is the problem? We have open loop transfer function, G of S. Okay. We should find gain margin, gain phase crossover frequency, phase margin, gain crossover frequency. Okay. So first what you do is you follow all these steps. Okay. So same steps and plot the magnitude plot and phase plot. Okay. The magnitude plot, you see, basically what we do, magnitude plot. Okay. From the magnitude plot, okay, we will find the phase crossover frequency. That means what? When the magnitude plot becomes 0, we'll say that is phase crossover frequency from the definition. Am I correct? Okay. Similarly, from phase plot, when that is equivalent to minus 180, we get this gain crossover frequency. Correct? Now these are the two things we got. Omega PC and omega GC. Using these two, now we have to calculate gain margin and phase margin. So directly we can calculate by using the formulas. The gain margin, okay, that is 20 log 1 by Z of J omega PC. At that point, it will become 1. So substitute that PC value here, you'll get 2 dB. I'm sure. So this is the one. Okay. Similarly, phase margin is 180 plus 5 GC. Okay. Similarly, what is 5 GC? From the transfer function, you have this 5. Substitute your omega GC there. So you're getting plus 5 degrees. Okay. This is your phase margin. Okay. So I hope this is clear. Okay. So when you see that, if you understand that basic if you understand these basic definitions, how we start with the phase crossover frequency, find the gain margin, start with the gain crossover frequency and find the phase margin. Then this is the same thing exactly we're applying there. Okay, so you should check these values because these are design. This is very basic for the design of the controller using the Bode plot. Okay. So here in this case, since both are positive, the system is stable. Okay. So I'll give this notes also. Check all the calculations, and if you have any doubts, you can ask me in the next slide. In the next slide, we will take up one problem and how to design this lead lag compensators. Okay, in specific, because that is the syllabus of this week 9. Okay, any queries? Any queries? So I'll give these notes also. I'll upload these notes in our Google Drive folder. Okay, do you have any queries? Any queries? Do you have any queries? If you have any queries, please feel free to ask them. Okay, if there are no queries, we'll stop here and continue in the next slide. We did the same design problems using the frequency response. Thank you.